Okay, so in the last example you did, I just want to emphasize that this is the case, these two component plots were the case where mu is less than 0. So this is the case where the equilibrium solution is a spiral sink. Of course, the component plots for a spiral source look pretty similar. Except this is the case in which the real component of your eigenvalue is positive. So if mu is positive, we might get a component plot that looks something like this. So instead of a exponential decay function that is controlling the amplitude of your cosine and sine functions, we have exponential growth. So the two component solutions then are going to oscillate between two functions that are exponential. So we'll have the exponential growth for e to the 2t in this example. And here's just a reflection of that over the t-axis. And the amplitude of this cosine function, right, will oscillate like a cosine function, but the amplitude is basically increasing with time. And it's going to oscillate between this exponential growth function. Likewise, for x2, we get a function that oscillates like a sine function, and in this case, the amplitude is going to oscillate between the e to the 2t and the reflection of that across the t-axis. Okay, so that is an example of the component plot for a solution that is for perhaps a spiral source equilibrium solution. Okay, now we looked at the case then where mu is positive, and so that's the spiral source. When mu is negative, that's where we have the spiral sink. We might ask ourselves, well, what happens if mu is 0? Right, so we've done sort of all the other cases, so that begs the question here, what happens when mu equals 0? Okay, so it is possible that we have a complex eigenvalue where we may just have a frequency component. Remember, nu here represents the frequency. That tells you how fast the trajectories sort of double back on themselves in the phase plane. Or you could think of the frequency as the number of times in which the function crosses the t-axis over a period of 2 pi. So if nu, in this example up here, nu is 1, but if we wanted to increase the frequency, we would just change the value with the t coefficient in the cosine and sine function. Okay, and then the function will oscillate more between 0 and 2 pi. So in this example here, lambda is only has a frequency component here. So there's no real component whatsoever for these eigenvalues. Okay, so how does that change the problem? Well, that means in our complex exponential, there really is no real component. So when we try to break this up, really we're breaking this up into e to the 0 times e to the plus or minus, forgot to multiply by t here, plus or minus I nu t. Okay, so this is really the radius term in your spirals here is staying fixed at 1, more or less. Whereas this exponential here, we can rewrite using Euler's formula. This would be cosine of nu t plus or minus I sine of nu t. Okay, so for your component thing here, again, this thing acts like your radius, and the radius is 1 in this case. So the radius remains fixed at 1. So if we were to again look at the phase plane trajectories, what are we going to get? Okay, well, this term here is remaining constant here. So if I have a unit circle here, it looks something like this. And suppose the real component looks something like this. We have x1 and x2. Here the radius is just 1. And let's just say for kicks that we have cosine t and 1 sine of t. Okay, well now this is just a plain old circle, right? This is just a plain old circle in polar coordinates, right? So at t equals 0, we're here. Okay, as t increases, the x1 component decreases and the x2 component increases. Okay, so what we're going to get is a circle, and in this case the trajectory is going to be counterclockwise. Okay, and right, the e to the mu t term is constant, right? So e to the mu t is 0 in this case, so the radius does not change with time. Okay, it's possible with different initial conditions, we might have different trajectories, right? So if I require my initial condition to be here, well then the so if that's t equals 0 for our initial conditions, then the c values that go along with the real component will change, and then the radius is whatever the c1 and c2 values may happen to be. Okay, so in this case, the general solution when mu is 0 is going to give you a collection of circular trajectories. Okay, and again, the exact radius depends on the initial conditions, and I'll put in parentheses the C1 and C2 values for this one. Now, for a little bit of homework, just so that you guys aren't following too passively along here, what I would like you guys to do is to go through example 2 on page 173. So I want you guys to sort of do the grunt work here. Go through that example in detail and analyze the kinds of trajectories you might get for this kind of equilibrium solution. Okay, of course, again, let's not lose sight of the fact here that our equilibrium solution is at the origin. In this case, here are examples of trajectories that do not necessarily cross through the origin. So it perhaps for this trajectory here, this neither starts or stops at the equilibrium solution. But it does sort of rotate around it. And in this case, the center of rotation is the equilibrium solution. And that actually, that's how we might classify this equilibrium solution. So we would call this a centered equilibrium, or a centered critical point if you prefer. And of course, this is an example of a stable equilibrium. And what kind of problems have centered stable equilibrium solutions? Well, it turns out that harmonic oscillators are examples of centered stable, and these generally occur, of course, when you're ignoring friction. And we will see a whole slew of examples like that when we get to chapter 4. So if we're a little light on examples here, we will make up for that when we get to chapter 4. So this is conservation of examples here. Okay. All right. And yeah, like the spiral source and spiral sink, again, we can look at the component plots for these. So what do? We plot plot the x1 and x2 components with time. Here it's really simple in this example. So if we have x equals r cosine of theta and x2 is r sine of theta. Let's see, here's pi over 2, here's pi, 3 pi over 2, and 2 pi. Right, these are just plain old sines and cosine functions. So here is our cosine function. Whoops. Should have drawn that a little better there, but oh well. So it's just a regular cosine function, and it oscillates between 1 and -1. That gives me x1. And then x2 is a plain old sine function in this example here. So this will look something like this. So here we are. All right, and so x2 here is in black. Right, and so the component plots are pretty darn easy for a centered, stable solution. Okay, so that pretty much rounds out section 3.4. The last bits of eigenvalue analysis that we haven't talked about are when we have repeated eigenvalues. So it is possible that your characteristic equation only has one root, but since it's quadratic, we know that the characteristic equation then must sort of bounce at that root. So that is sort of our one remaining example that we are going to talk about, and that is the beginning of section 3.5. Okay, so the last part of this lecture, Tuesday's lecture, we are going to start talking about section 3.5, and this handles the case where we have a repeated eigenvalue. And I've gone through a little bit of this mainly because my video froze up, so I had some technical difficulties here, but I'll recap what we did. I went about 10 minutes before realizing my computer was frozen. So anyway, again, so let's suppose we have our system, our linear system of first order ODEs. X prime is equal to AX. And of course, we know that the eigenvalues of this system can be found using the characteristic equation. So what do we do to get the lambdas? We find lambda squared minus lambda times the trace of A plus the determinant of A, set it equal to 0, and find the roots of this equation. So if we let the left-hand side of the characteristic equation be p lambda, we'll just say that's a polynomial with respect to lambda. And so we'll call this the characteristic polynomial. And we know that this polynomial is going to be a parabola for a 2x2 system. And we get repeated eigenvalues when the characteristic polynomial intersects the horizontal axis, or lambda in this case, only once. So this is the case where you've got a parabola, and it only has sort of one intersection point for the independent variable. And we know that this is from Calc 1 and Calc 2 that this is the case where you have a double root. So this is where the parabola bounces on the horizontal axis. as opposed to a parabola, say, that intersects at two distinct points on the horizontal axis for lambda here. So this is the case where you have a double root. Now it turns out that systems like this, our homogeneous linear system of first order ODEs, have eigenvalues that have a double root like this when the system matrix is diagonal, as it turns out. So in the example in your book starts with the example here where your linear system has a matrix where you have negative ones along the diagonal. And you can imagine generating other systems that have repeated eigenvalues, or that is double roots in the characteristic polynomial, using a diagonal system matrix. So in this example, let's go through and find the general solution and see what kind of trajectory curves we might get from this. Okay, so again, we just start by finding the eigenvalues, and hopefully, as promised, we will get something where we have repeated eigenvalues. So what we do is we set up the characteristic equation. In this case, it's just going to be lambda squared minus lambda times the trace of the system matrix, and the trace in this case will just be -1 plus -1. And to that we'll add the determinant. In that case, the determinant will be -1 times -1 minus 0 times 0. And in this case, the characteristic polynomial that we get is going to be lambda squared plus 2 lambda plus 1. And that, of course, we can factor here. This is going to be lambda times lambda. And in this case, this will just be lambda plus 1 times lambda plus 1. Okay, so this is where we have lambda plus 1 squared. So this is the case where we have a double root to the characteristic polynomial. Okay, so what does that mean? Well, that means we have a repeated eigenvalue. And then in this case, lambda equals -1 is a repeated eigenvalue. So we say lambda 1 is equal to lambda 2, and in this case, in this example, it's -1. All right, so there we go. Onward. Next step, of course, is to find the eigenvectors. And this may seem a little silly, but might as well just go ahead and do it. So what do? We let lambda 1 be -1, and we solve the system a minus lambda 1 times v1 equals the 0 vector. That will allow us to find the vector v1 that corresponds to lambda 1 equals -1. Okay, what do we get? So we're going to have -1 minus -1 for this matrix here. And we'll have -1 minus -1. I'm just subtracting lambda from the diagonal of A. And then our vector v1 will have components v1, v2, and that's going to be equal to the vector 0, 0. Okay, and what do we get? Well, we get something kind of goofy here. We get the matrix 0, 0, 0, 0 times v1, v2 equals 0, 0. So this is a rare case where both components v1 and v2 are arbitrary, right? It doesn't matter really what we choose for v1 and v2. v1 and v2 are arbitrary. Okay, so any old vector v1, any old vector will do in this case. So we could have any eigenvector that we wanted, as it turns out. Now, in terms of finding a general solution, though, we would like at least, we need at least two vectors, right? So it could be anything really what we wanted. But we want two vectors, and most importantly, we want those two vectors to be linearly independent. Okay, so so the vector v1 is arbitrary. Okay, and likewise for lambda 2, v2 is also arbitrary. Okay, of course you'll get this, you have the same eigenvalue, so you're going to get that zero matrix again. Okay, so what we're going to do is we're going to choose two linearly independent vectors for v1 and v2. Okay, if we choose them to be linearly independent, then we can formulate a general solution, essentially, is what that's saying. So we're going to choose v1, we'll just make our lives easy. We'll say is the vector 1, 0. Okay, and an obvious linearly independent vector to that will be the vector 0, 1, right? So we showed, this is an example that we did before. So these two are definitely linearly independent. Of course, if you're unsure of that or unsure of yourself, you can always double check that, right? You just make sure the Wronskian determinant formed by these two vectors is equal to 0. And it is. Or sorry, is not 0. And in this case, yes, it's going to be 1. All right. Okay. So there are our eigenvectors, right? Not a whole lot of work that really had to be done. Okay, so let's find the general solution. Okay, so our general solution then will be the vector x equal to c1 e to the lambda 1 t times v1 plus c2 e to lambda 2 t v2. Okay, in this case, both the eigenvalues are negative 1, so this will be negative t. v1 will be 1, 0, and c2 will be e to the negative t 0, 1. So there is our general solution. Okay, so let's look at the limiting behavior. Okay, so here's our solution, and of course the question we should be asking ourselves is, so what? So let's try to generate a few trajectories from this result. So we're going to do that by looking at the limiting behavior. So to do this, again, what we do is we look at one of the eigenvector solutions and we look at the other eigenvector solutions. So we look in the case when one or the other is dominant. Okay, so when v1 is dominant, what do we get? So we'll have something like x x1, right, equals c1 e to the negative t 1, 0. So that's when the x1 term takes over. Okay, as t gets very large, this goes to 0. And so x of t, the general solution is going to be approximately c1 times 1, 0. Okay, so what does this tell us? Well, this tells us that the x component is 1, the x2 component is 0, or c, whatever. If we want to ignore the c, we can do that as well. Okay, and then in this case, x2 is going to be 0 times x1. Not a particularly interesting result. Okay, so in the phase plane solution, we can plot that line. What is that line? Well, it's the zero line. So this is the when x2 is 0. So this is the horizontal axis. Okay. When v2 is dominant, right, the x2 vector is essentially taking over. Looks like this. So then we say the general solution is approximately c2 0, 1. So we have x1 is equal to 2 and x2 is equal to 1. I suppose I could use the same plot here. Why don't I do that? Whoops. So we'll just plot this up here. So x2 equals 1. All right, so, and in this case, of course, it doesn't have really anything to do with x1. Okay. All right, so what do we get? All right, so this is the case when x1 is 0, right? We get basically a vertical line in this case. Okay, so that should be true for all x2. Here, I suppose we have to not ignore the c2 in this case. All right. So there we go. Those are our two lines when we have a repeated eigenvalue. Okay, the limiting behavior is both the horizontal and vertical x-axis in the phase space or the phase portrait of the solution. Okay. All right, so why don't we end there, and we'll pick back up there on Thursday.